Here are the differential equations for the angular momentum of a tumbling box. Try throwing a book or a box or any rectilinear object whose 3 dimensions are all different into the air with a twist to make a tumble. You can get it to rotate about its longest axis or about its shortest axis, but you can't get it to rotate about its middle axis. Let's examine that phenomena numerically. Here's the anonymous function defining those system of 3 first-order differential equations. Now I'm going to start with an initial condition that's near the first critical point. 1, 0, 0 is a critical point, and I'm going to take 0.2 times a random number so it'll be near the critical point, and then normalize it so that it has length 1. So the largest component is the first component, and the other 2 are small but not too small. This is an easy problem numerically. There's no stiffness involved here. So I'm going to use ODE 23. Integrate from 0 to 10, and here's the solution. The blue component is the first one, and it stays near 1, and the other 2 are periodic, rotating around 0. Let's go back and take another starting condition. Here it is again. Now the other 2 components are really small, and when we integrate that, the blue component stays flat near 1, and the other 2 guys hardly move at all. Now I'm going to go to the third critical point, 0, 0, 1. Do the same thing. Take a random number near there. Use ODE 23. Now the yellow component stays near 1, and the other 2 move periodically around 0. Run that again. Third component is near 1. The other 2 are not too big. And run ODE 23. The yellow component stays near 1, and the other 2 rotate periodically around 0. Now we're going to go to the middle critical point. We're going to try and get the box to rotate around its middle axis. The second component is the one near 1. And now we see completely different behavior. This sienna component doesn't stay near 1. It goes down near -1 and comes back up. Let's integrate over a longer period so we can see that behavior. So it's periodic, but it goes down to -1 and comes back to 1. And the other 2 move in large amplitudes around 0. So this is the instability of that middle critical value. Let's do it again. Same thing. 1 down to -1 and back up. It's periodic. These solutions are all periodic, but that middle critical point is unstable. Now I want to view these in a different way graphically. The differential equations have these 3 critical points. Any solutions that start exactly on these initial conditions stay there. But what happens if you start near these initial conditions? Well, it turns out that X and Z are stable critical points, but y is an unstable critical point. If the angular momentum is near x or near z, it stays near there. But if it starts near y, it moves away quickly. You can think of x as the short axis and z is the long axis. Rotation near the short axis is stable and rotation near the long axis is stable, but rotation near the middle axis is unstable. We can see that in the following graphic. It turns out that if a solution starts with an initial condition that has norm 1, it stays with norm 1. So the solution lives on the unit sphere. Here's our unit sphere with our 3 critical points, x, y, and z. If this were the Earth, the z would be the North Pole. X is where the 0th meridian crosses the equator. That's in the East Atlantic, a little off of West Africa. Y would be where the 90th meridian crosses the equator. That's in the Indian Ocean, west of Sumatra. If we start with an initial condition near x, the solution orbits around x. That's stable rotation around the short axis. If we start with an initial condition z, near z, the solution orbits around z. That's stable rotation around the long axis. But if we start near y, the solution takes off, goes over to near minus y, turns around, and comes back to y. Periodic, but goes clear around the globe. That turns out, that's a circle, actually, an orbit around x. If we come up a little above y, we get an orbit around z. Go down a little below y, we get an orbit around minus z. Go to the right of y, we get an orbit around minus x. Let's zoom in a little bit. And we can see that y is a classic unstable critical point. Let's conclude by drawing a few orbits.